welcome everyone for this year's last TDS webinar. And it's my great pleasure to introduce Professor Nathan van der Wouw, who is from Eindhoven. And Nathan got his degrees at the Eindhoven University of Technology, and he's currently a professor and the leader of the Dynamics and Control Group in Mechanical Engineering. And Nathan and I think, first met personally about 8-ish years ago in a conference in Ann Arbor. And I had two impressions at that point. So the first one, I went to his talk, and then I came out, wow, this is a fantastic talk. So it was really great and informative and clear. And the second thing was that we had a discussion in one of the breaks. It was a very busy conference, but he found the time to sit down with me and discuss research, and it was really inspiring for me talking to someone of his stature at that point. If you look at his recognitions, he has numerous awards from IFAC. He's on also many editorial boards. He's a senior editor. He's a IFAC, an IEEE fellow. So I don't want to get all those details. I think you can read it in the bio. Instead, I would like to give the floor to him. And please welcome Professor van der Wouw. The floor is yours.
Well, Gabel, thank you very much for the nice introduction and also for the invitation. I'm very happy that I can share some of our research results of the past years on model reduction for delay systems. And it's really a pleasure for me to address this expert community on delay systems, as I do not necessarily consider myself an expert on delay systems. So I hope I can share some interesting results with you. The results that I'll be discussing have been achieved over the past years with several collaborators, amongst which also Wim Michiels, who I know is present, but also Antoine Chaillet, Superlec Central in Paris, and Bart Besseling, but I'll pay due to them later on. So I want to discuss some results on model reduction for delay systems. And let me first go over the outline of this talk. So after an introduction where I hope to briefly motivate why we should be interested in complexity reduction for systems with delays, I want to formulate the problem that we have considered more precisely. And then the core of the talk will be about two model reduction approaches. One is a decomposition approach, where we decompose the delay system in a finite dimensional part and a delay operator part as a basis for model reduction. And then secondly, I'll discuss both delay dependent and delay independent approaches for really balancing approaches for model reduction for delay systems. And then throughout, I will, through some examples and also some brief case studies, illustrate the benefit of these approaches and close with some conclusions. Okay, now for this community, I think I don't need to motivate why it's interesting to look at delay systems. These are just some examples in these pictures of engineering applications that I've worked on, which involve delays. One of them is manufacturing systems. I think high-speed milling and turning processes have been, well, studied a lot in the scope of delay systems. I've been working quite a bit on drilling systems, which delay enters in exactly the same way, namely through cutting processes. In drilling systems at the bit, whereas in high-speed milling, it's the cutting process between tool and workpiece. Another example that I've been working on a lot is network control systems, where the delays enter through communication delays, for example, between actuators and a controller, or between sensors and a controller. Now, what is also characteristic to these systems is that when you develop models, they typically are of high dimension, so involve many states or many degrees of freedom. So in this example of this high-speed milling machine, there are typically structural dynamics involved of the tool, of the spindle, which comes from, for example, finite element modeling or experimental modeling. Then in the drill string, you have high-dimensional models, for example, coming from this spatial discretization of wave equations describing the the vibrations of the drill string. And in network control, it could be high-dimensional models of the complex plant that you're trying to control over the network. So this inspired us to think about, can we think about doing complexity reduction for such high-dimensional systems, which also inherently involve delays? Now, many people have looked at the model reduction for delay differential equations. I must say that, let's say, the field of model reduction for delay systems is significantly smaller than for ODEs. But quite some people have thought about this problem. This slide is by no means meant to be complete or exhaustive, but I want to highlight at least a lot of work on linear delay differential equations has been done. I want to distinguish between techniques that try to reduce complexity of these models by going to finite dimensional approximations. So approximations typically in the form of not DDEs, but ODEs. And also techniques leading to reduced order delay models. So these are models which preserve the infinite dimensional nature of the original delay system. And there are works on moment matching techniques for delay systems at Imperial College by Giordano Saccarciotti. There are optimization-based methods in the early 2000s. There's recent work more on iterative Krylov-based methods. So there's a lot of interesting work there. And I'll try to position a bit what our contribution is to this field later on. Then there are also works on nonlinear DDEs. Some works of Giordano Saccarciotti and co-workers on extending these moment matching techniques to nonlinear delay systems, and also some recent work on finite dimensional approximation for bilinear DDEs. Now, let me sketch the high-level problem that we want to tackle. So we want to pursue model order reduction for delay differential equation, mostly focusing on linear retarded DDEs with constant delays, but also discuss some small extensions to a class of nonlinear DDEs with time-varying delays. And what is essential to us is that we want to preserve the delay nature of the system. We also want to preserve stability properties of the original system during reduction. And we want to provide an error bound, which means we want to be able to say something about the quality of the reduction. Okay, then I want to discuss two distinct balancing-based approaches. One is a decomposition approach, which first separates the delay part from the finite dimensional part of the dynamics, and then actually employs reduction techniques for finite dimensional systems. And then still we'll try to say something about stability preservation and error bounds for the reduced delay system. And secondly, I want to discuss what I would call a true balancing approach, which really performs reduction directly on the delay system itself. Now, this decomposition approach, if you're interested, you can find more information in these papers, in which also Bart Besselink and Wim Michiels were involved. Okay, so then let's get started. So in the scope of this decomposition approach, we consider a delay differential equation of this form, where we have state X, an input U, and an output Y. And you see here a term related to the current state at time t, but also a part depending on the state at a delayed time t minus tau, where tau is now a constant delay. Now, so the purpose is ultimately to be able to present a reduced order model. And with that, we mean, so consider here the state at time t to be in Rn. So this is just a system described by n delay differential equations. And we want to reduce it to a model with a reduced number of differential equations. And so the reduced order model will still be infinite dimensional, but described by a reduced number of delay equations. Now, as a first stepping stone, let me transform this linear DDE to this form here, where this matrix A0 is now the sum of these two matrices A0 bar and A1 bar. And there is an additional part which is now not only dependent on xt minus tau, but is actually related to the difference between xt and xt minus tau. So it's related to the evolution of the state in the delay interval. And it will come later on. It will become clear later on why we do this. Okay, so then again, the purpose is to construct a reduced order DDE, sigma hat, with a number of delay equations n hat, which is smaller than n, typically quite a lot smaller for the purpose of reduction, which still approximates the input-output behavior, so from input U to output Y accurately, and preserves stability properties for this delay system. And then as a second extension problem setting, we want to consider a nonlinear variant of this problem, where you see that the delay part is now given here. And now we have this nonlinear function f, which depends not on the full state, but on some output z, which is a function of the state. And here you also see this term z at the current time, minus z at a delayed time, where now we could consider not only constant delays tau, but also time varying delays delta tau of t. And the purpose of the reduction is exactly the same as before. Okay, now let me go back first. So what we're going to do first in this decomposition approach is to rewrite this linear DDE in terms of a feedback interconnection between a finite dimensional LTI part and a delay operator part. And in order to do so, we're actually going to reformulate this part, A1 times x of t minus xt at t minus tau. Now in this term, so remember this term, we're going to actually capture it by this term here. So here you have the same equation, but here you see that the part related to the delay is now reformulated here. And let me explain this a bit. So this v of t is now given as an integral from t minus tau to t of a variable w, where w is the time derivative of z, and z is some function, some linear function cz of the state x. Now, given the fact that w is z dot, this is actually just this output z at time t minus z at t minus tau. Now, if you look at this right block here, you see that the product of bv times cz is exactly a1. So this term is exactly a1 times the difference of x at the current time minus x at the delayed time. So this feedback interconnection still represents exactly the same dynamics as the original linear DDE. But it is now written in terms of just a finite dimensional nth order LTI system with input U and input V. If you look at this block scheme here, and outputs Y, the original output, and output W, which is Z dot. And then we have this delay operator part here, which transforms W into V. Okay, then in the nonlinear case, it's exactly the same, but now this delay operator part becomes a nonlinear delay operator with this nonlinear function f, and it might depend, the delay interval might depend on this time varying delay delta tau of t. Okay, now what we intend to do, well, let me first go back to the applications to explain what people do in practice. So in practice, what people typically do in engineering is that they just build this model for this drilling system, and you might have a finite element model for the drill string dynamics in different modes, and you have some constitutive model of the bit-rock interaction where the delay and all kinds of nonlinearities enter. So typically what people do, they just produce this finite element model to a desired order and reconnect this nonlinearity or this cutting process which induces the delay. So this is quite common practice, but the question is when and why this is actually a good approach. So this actually inspires this approach where we only reduce a finite dimensional linear part and leave intact the nonlinearity and the part that induces the delays. The important thing to mention here is that we will consider to reduce this linear finite dimensional part, taking into account not only the original input u and the original output y, but also the input-output pair v and w that comes from writing the original DDE in this feedback interconnection with this delay operator part. So we know that our reduction needs to be predictive with respect to both inputs and both outputs.
Excuse me, Nathan. Hello, this is Emilia.
Sorry?
I have a question. Probably I have missed something in the previous slide. Can you go here? I see that W from one side, it is Z dot. Yes, W is Z dot. But in the second line, it is like output. Is it related one to the other?
Yes, so it's actually, if you comply, let's say, to the definitions of all these matrices on the right side, you can see that it's actually the same.
Ah, okay, thank you.
Yeah, so you can just use compute C dot, right, which is CZ times X dot, then you substitute this. And if you then use all these matrix equalities here, you can see that you also comply with this output definition of W.
Okay, thank you.
Thank you for the question. So then the idea is the following. We have this feedback representation of the original delay dynamics. And the only thing we do is we now keep the delay operator intact. And we reduce this finite dimensional LTI dynamics to sigma 1 hat. Now we're going to use the fact that for this reduction of the finite dimensional linear part, there are many techniques available. For example, the well-known balancing-based techniques that go back to Moore and Glover, which actually preserve stability and provide an error bound on the reduction of only the LTI finite dimensional part. But we want to guarantee that we can also say something about accuracy and stability preservation of the delay system as a whole. Now it's important to note that obviously reducing the state dimension only is going to be effective when the number of delay equations is significantly larger than the number of output and input variables that you have, which relates to the fact that we assume that that this matrix A1 is of relatively low rank. Well, meaning that the number of variables which are actually associated to entering the delay in the equation is lower than the state, the number of equations in the DDE. Okay, now then we need a few assumptions as a base for our results. The first one is that the linear finite dimensional high order system sigma 1 is asymptotically stable. Now the second condition that we have is a small gain condition given here, gamma VW times tau is smaller than 1, where this gamma VW is the input output L2 gain of this finite dimensional part from input W to output V, and tau is just a gain of the delay operator block in the linear case of our problem. So basically it's a small gain condition for this loop here. Now then in the nonlinear case, then we need a small gain condition of this form, where now instead of tau you have L times this tau plus some square root 7/4 times mu. And this is again a small gain condition, but now it involves L, which is a Lipschitz constant on this nonlinearity F. And this tau plus this term here is a gain bound for the time varying delay operator, which is taken from literature, where we assume that this time varying delay has in absolute value a bound mu. Okay, then this slide said more assumption, but actually they're not really assumptions, that these are more conditions that we can easily satisfy. So the third condition is that the linear finite dimensional reduced order system is also asymptotically stable. Well, if you use standard balancing techniques, then this is immediately guaranteed. And the second is that for this reduction of the LTI finite dimensional part, there exists an error bound. Now here it's formulated in an incremental sense, but for linear systems, that actually doesn't matter. So let me explain what this means. So these operators F here are just operators from inputs U and V to either output Y or output W. So from both inputs to both outputs. And this epsilon are just errors between the output Y or W of the full order system or the reduced order system with a hat. So these E are just error operators. And what this equation just says, if we would go to a non-incremental version, it would be that we have finite gains from L2 signal norms in input U and V to these errors. And for balancing-based techniques, these error bounds are readily available. Okay, now then let me formulate the first result, and not so much by copying the mathematical theorem, but just more in words. So under these conditions, we can guarantee that we have preservation of L2 gain stability and of asymptotic stability when the input U is 0, if a robust small gain condition is satisfied. So remember, we had already gamma WV times tau smaller than 1. If we now have a robust small gain condition where this epsilon WV plays a role, where this epsilon WV is the error bound associated to the error made in the reduction of the LTI finite dimensional part from input V to output I is W. And so this is just the reduction error made in the balancing-based reduction of the LTI finite dimensional part. Now, secondly, so this is stability preservation. Secondly, we have an a priori error bound. So the error on the output prediction in an L2 norm is smaller or equal than some epsilon times the L2 signal norm of the input, where this epsilon, I'll give a more explicit expression on the next slide, is dependent on the delay tau, or also on this mu in case of these time-varying delays, on the reduction error bounds of the reduction of the finite dimensional linear part, and in a nonlinear case, potentially on the Lipschitz constant L. But you can compute it a priori without actually performing the reduction. Now, how does this look in the linear case? So this is an expression of this error gain bound, depending on the epsilons. All the epsilons you see here are error bounds you can compute in case of linear balancing of the finite dimensional part. You see it depends on the gammas, which are just gains of the original high order system, and tau, which is the delay. So two remarks are in order here. This error bound can be made arbitrarily small by making the reduction of the finite dimensional part accurate enough. So if you make all these epsilons smaller than all these terms become as small as you would want. The second part is for small delay. So if you let the delay go to 0, then this term becomes small and this term becomes small, and you're only left with the first term, which is exactly the error bound that you get in standard LTI finite dimensional balancing. And so you recover the case without delays. Okay, then another remark is in order, because one of the goals I set myself was the preservation of the original delay structure of the model. Now remember, if we go back, what we are left with after reduction is a reduced order LTI system in feedback interconnection with a delay operator. And so this is the form of the system description we get after reduction. And so it's actually a system in this form. But we want to go back actually to a system of this original form. That's what this slide is about. So let me go fast forward again. So for the linear case, the reduced order delay system in this feedback interconnected form can be cast into the original DDE form, or the same form of the original high order system, if the linear finite dimensional part is reduced using balanced residualization. So this is a form of reduction by balancing using a singular perturbation-based approach, which makes the reduction exact at frequency 0. And in that case, we can show that we can really rewrite it back into the original form. Now, for the nonlinear case, that's immediate, because the system in feedback interconnection form is actually immediately in the original DDE form. Okay, now let me give a simple example. This example is inspired by this manufacturing example. And I'm sorry that apparently the resolution of the picture is not very good. So if we would write down models for such, let's say, models for turning or milling, they would typically have this form, where on the left-hand side, Q would be generalized coordinates of a structural dynamics model of the tool and the spindle. So in this picture, I have a very simple representation of this. So consider this machine and tool to be represented by this simple structure here, which could vibrate up and down. Then this left-hand side would just be a second order representation with mass matrix, damping matrix, and stiffness matrix of that structural dynamics. Now U could be an input, for example, a force, maybe in a spindle actuator that could be used to try to suppress vibrations. And the second term would be related to a forcing term related to the force induced by cutting away the material by the cutting tool. Now imagine this tool passing over the workpiece in this direction, and maybe some time ago, it took the previous pass over the material and left behind this wavy surface here. Oh, sorry. Now in the next pass over the material, this cutting tool is a bit deeper into the material to remove some material. And now it follows this dashed line. Then the depth of cut here that the tool sees is this delta, which is exactly Z, which is the position of the tool at the current time minus Z at the previous time, which is exactly this difference here. And then typically the force depends on that depth of cut, and the typical models used in milling or turning are typically nonlinear models that relate this depth of cut to the force on the cutter. So you can easily see that we can translate, if we go to first order form, we can translate this to DDEs in the form that I have introduced before. Now in this case, the high order dynamics is related to the structural dynamics of the tool and the machine. This nonlinear delay effect comes from the cutting process, and these models are typically used to analyze, for example, chatter vibrations in these manufacturing processes. And there are many people, like Altentas, Gabel Stepan, and co-workers that have worked a lot on these type of models and the analysis of these type of chatter vibrations. Now, we've also worked on this, and we saw it's very helpful if we can reduce these models for the purpose of stability analysis and also controller design. Now, to take a simple example, if we would take a model of order 20 for the structural dynamics, and we would look at, this is not entirely correct, I now see here. If we take the frequency response function of that structural dynamics from the force on the workpiece to the velocity z dot. So I guess it is correct. Then you see this black frequency response function. Now, if we now take the most extreme reduction to order 2, and we only capture the first resonance, you get this gray frequency response function. So this is the reduction of the finite dimensional LTI part. Now, this dashed line indicates a bound on sigma hat 1 that we could get from just an error bound of the linear reduction. Now, if we then reconnect this reduced order finite dimensional system to the delay operator, to the nonlinear delay operator describing this cutting process, and we would do simulations for a particular type of input and simulate the depth of cut, which is z minus z at the delayed time, then you see that this reduced order model still accurately predicts the depth of cut evolution. Now we can also compute an error bound. Now, if you combine this input level with this error bound, then you see we would get, let's say, errors in the order of 100 micrometers, and you see that the actual error evolution is quite a bit smaller, and that's due to 2 facts. One, this error bound can indeed be conservative. The other fact is we did not excite with this input the system fully in resonance. So if we'd excited with different frequencies, we might see actually higher errors than the ones we see here. Okay, so to wrap up on this first approach, this decomposition approach is applicable to linear and also some class of nonlinear systems, and to constant and in some case to time varying delays. It's structure preserving in the sense that you preserve the infinite dimensional delay nature of the system, and we have preservations of input-output properties, and can give an a priori error bound saying something about the quality of the reduction, and also give some insights on what knobs you can tune in terms of the original dynamics, the delay, and the error bound of the reduction to reduce this. Now then I want to go to a second approach, which is a balancing approach for delay system. For those of you interested, your best reference would be this 2020 Automatica paper of a PhD student of ours, Sajjot Naderi, and this is work together with Bart Besseling and Antoine Chaillet. So, and I want to start with a delay-independent version of this approach as a stepping stone, and then I'll go later on to a delay-dependent version. So let's start again with a delay system denoted by sigma with inputs u and outputs y, described by this delay differential equation here, where now we have matrices A and AD associated to the non-delay and the delay part. Now we consider now only constant delays and a bit of notation, which is probably very familiar to you, that we denote by x subscript t, actually just the state function segment in the delay interval. And the initial state segment I'll denote by phi. And now the assumption that we'll take is that this system is asymptotically stable as a basis for reduction, because that's a property we would like to preserve. Now then, the problem statement is that we want to find, given sigma, another delay differential equation sigma hat, now with a state xi, where the number of delay differential equations here is k, which should be smaller than n, which is the original number of delay equations. I want to find this delay differential equation that well approximates the input-output behavior of the original one, and preserves the infinite dimensional nature of the delay, which is natural because we still have this DDE here, and which preserves stability. Now, so we want to preserve stability, so this DDE should be stable. And again, we want to find an error bound, which of this form, such that the error in the output prediction, so y hat compared to y, should be smaller than some epsilon times the L2 norm of the input u. Now, in this case, we're not going to do this decomposition into a finite dimensional part and a delay operator part. We're going to look at the DDE as a whole, and to recall that standard balancing techniques for finite dimensional LTI systems, the basis for that is 2 key objects, which are 2 energy functions, an observability energy function and a controllability energy function. And we'll do the same for delay systems here. So the observability energy function tells you something about the output energy that you get if you set the input to 0 and you initialize the state at the initial state phi. Yeah, so you initialize the system and just look at the output energy that you get. And it tells you something whether particular initial states lead to a lot of output energy or you hardly recognize them in the output. So it's a measure of observability looked through the eyes of output energy. Now for finite dimensional LTI system, this output energy or observability energy function, in that case it's a function, can be characterized by this quadratic form of the state, where this matrix Q is associated or can be found as the solution to this Lyapunov equation. Now, in this case, in the case of DDEs, it's not an observability energy function, but a functional because it depends on these initial function segments phi. Now, because we have assumed our system to be asymptotically stable, it can be shown that this observability energy function is always bounded. Now, to make the step towards DDEs, at least in this first delay-independent case, the first result is the following. If there exists positive definite matrix Q and a positive semi-definite matrix QD satisfying this matrix inequality, which probably many of you would recognize as a matrix inequality also used in the scope of delay-independent stability analysis for DDEs. If you find Q and QD as the solution of this delay-independent LMI, because the delay is not appearing here, then the functional defined here consisting of two terms, one related to the state really at 0 and one depending on the state in the initial delay interval, then this functional is an upper bound to the original observability energy. And so why do we do this? In balancing, typically we normally use the actual observability energy as a basis for balancing the realization of the dynamics. Well, here we don't know how to characterize this observability energy functional, but we know how to characterize an upper bound EO of this observability energy functional. Now, let me later explain why this is useful. Let me first do the same on the controllability side. So a controllability energy function or functional in our case is defined as the minimum input energy that is needed for an input U to take you from initial condition 0 at t is minus infinity to an initial state phi. Now, for finite dimensional systems, this optimal input energy can be characterized as a quadratic function of the state, characterized by some matrix P, which is the solution of a Lyapunov equation. Well, in our DDE case, we don't know how to characterize this controllability energy functional, which again is a functional due to these segment phi. So that's why we also try to characterize a bound on the controllability energy functional. And that's where we introduce this result, where if there exist matrices P and PD satisfying these inequalities, then the functional given here, again, consisting of these two terms, where the matrices R and RD relate to matrices P and PD, which are the solutions of these inequalities, such that this functional EC is a lower bound for the controllability energy function. So now why are these bounds useful? So let me go back here. So typically in standard balancing, you want to preserve states in your reduced order model, which lead to a lot of output energy, or in other words, you want to throw away or discard states in your model that have low output energy. So if there are states for which this EO is very low, then we know for sure, because of this E being an upper bound to LO, that also in the real output energy, the output energy will be low for these initial states. So these initial states are directions, are very good candidates to discard from your dynamics. And the same for the controllability side. So typically in standard balancing, you want to throw away states for which you need a lot of energy in the input to actually arrive at those states. Now, because E is a lower bound of L here on the controllability side, if you need a lot of energy in E, and so the energy is high for particular initial states, then you know also LC is going to be high, and it's best to discard those type of states in your reduction. So this is just more the intuition how we're going to use these bounds. Okay, as said, yeah, many of you might recognize these type of linear matrix inequalities from delay-independent stability analysis for DDEs, where we are going to use these for reduction. And the main idea is to perform balancing, or at least what we'll call partial balancing, using these matrices Q and P, which are the solutions of these matrix inequalities. Now we choose this standard result, which is also used in standard balancing for finite dimensional systems, which says that if Q and P are positive definite, then there exists a coordinate transformation used to transform the dynamics from the original to the balanced realization, such that after transformation, these matrices Q and P are both the same and diagonal, block diagonal, where these sigmas are the so-called singular values, and they are ordered. So sigma 1 is high and sigma Q is low. So in these transformed states, the states related to this first block are related to states that are easy to observe and easy to control. So these are the states you want to keep in your reduced order model. The states related to this very low singular value are states that are very hard to observe and very hard to control. So these are the ones you want to throw away. Now, using this idea, what we're going to do is, after we have computed this matrix T, and we've put this realization in balanced form, we're going to partition the state into x1 and x2, where x1 is of dimension k, which is dimension we want to reduce to, the number of delay equations we want to keep. And we're going to partition the system equations in a similar form. And then we just do truncation, which means we only are going to keep this matrix A11 times xi, AD11 times xi at the delay time, plus B1 times U, and the output y hat is only C1 times xi. This is classical truncation. Now, and the nice thing is that the energy functionals of this system can be characterized in terms of the original energy functionals, and all the bounds that we have on those can be reused for the reduced order system. Now, then we get two results, one on stability, one on error bound. The first one says if you pick K such that it is the sum of Mi for some R, and let me go back to the meaning of these M's. So the M's are the dimensions of these blocks here. So we have to reduce between these blocks of this matrix sigma. So not halfway or somewhere else. But this is exactly the same as for balancing for LTI finite dimensional systems. If we do this, then we can guarantee that if we reduce in this way, that the reduced order system, delay system is also asymptotically stable. And under the same condition, we can guarantee that the L2 norm of the error is upper bounded by the L2 norm of the input, or sorry, L2 norm of the input times some error gain epsilon, which is 2 times the sum of the discarded singular values. So the singular values of this matrix that we discard by reduction. And this error bound is exactly the same as for the finite dimensional LTI case. But of course, we compute our matrices P and Q in a different way. Okay, let me go to an illustrative example, which is actually an example that was taken from a paper of Wim some time back, which is a partial differential equation where V is the temperature of a heated rod, X is the spatial coordinate, T is time, and it's just a heat equation for a rod with a distributed heating source and also some delayed feedback. And because of that delayed feedback, you see here a delayed term appearing. Now, we have some boundary conditions, of course. We have a heat source at the middle, and the output is the average temperature of the rod over the spatial domain. And when we now do discretization of the PDE, we arrive at a model in terms of a DDE with 35 delay differential equations. And if we do the most extreme reduction to one delay differential equation, then for all the parameters given in this example, you arrive at this scalar DDE. Now, then if we look at the frequency response function from input, so from the input U to the output Y, then the original model gives you this black line. Now, if we go back to the order 1 DDE, we get the red line. And for me, this is a good example of the power of just preserving the delay nature of your system in the reduction. Because if we would have had to describe, let's say, the black frequency response function by any finite dimensional approximation, we have needed a lot more orders to describe this type of behavior, which is just immediately well captured by preserving the delay nature of the system. Okay, if we then look at the error bound, if we compute the error of the frequency response function between the original and the reduced order model, then the real error is given in black as a function of frequency. And the error bound we computed is the dashed line, which, as you can see, is conservative, but actually not all that much. So in this case, it actually can be really used as a measure for accuracy. Okay, so this is about the delay-independent variant, and now I want to introduce a delay-dependent extension to this. And I see I only have 5 minutes left. So now we just go to the case where you have exactly the same type of system form. In this case, we only assume that the system is asymptotically stable in some delay interval. And then we again need to characterize these observability and controllability energy functionals that I introduced before. Now, the only difference here is now we want to find matrices Q, QA, and a constant alpha O as a solution of this linear matrix inequality, which now depends on the delay. So these solutions Q are going to depend on the delay. And if we find these solutions, then we can construct a functional EO of this form, given here, which is again an upper bound of the original observability energy function. And similarly, for the controllability energy functional, we can find matrices P and PA and a constant alpha C, which are delay dependent, such that we can find a functional EC, which is a lower bound to the original controllability energy function. And now we can use these energy functionals in exactly the same way as before to construct a balanced form. Now, this is exactly the same as before. I want to emphasize that we would call this a partially balanced form because we only use the matrices P and Q as before. Well, actually these P and Q, so R is P inverse, and Q is given here, only characterize these first parts of these bounds on the observability energy function. Yeah, so we We don't at the moment know how to use all these terms to arrive at some other form of a balanced form. Now then, the reduced order system can be obtained by truncation, as I said before, and we have to realize that P and Q depend on the particular delay because the LMIs are delay dependent. So also this transformation matrix is delay dependent, and also the error bound will be delay dependent. And so then we get two results. First, if we put sigma in partially balanced form and this original system is asymptotically stable, then if we truncate in the proposed way, then we preserve asymptotic stability. Secondly, if we satisfy these conditions and we need a technical condition that these two alphas are the same, then we again have an error bound of exactly the same form as before. Now let me close with an example. So this is just a simple example, not going to introduce the numerical equations. But if we look at these singular values, how they decay, so this is a sixth order original system, but we're going to reduce to 2. And this is the way how these singular values decay. We can compute the error bound for the delay independent case. So here you see it doesn't depend on the delay, but if we compute the error bound for the delay dependent approach, we can get much tighter bound on this error gains. So that gives you the benefit of the delay dependent result. Now, if we then look at the original frequency response function from input to output in black, then if we use our original decomposition approach, you get the blue line. The delay independent approach gives you the red one, and the proposed approach, the gray one. And you can also see at the bottom the actual associated errors that you get. And you also see that an error bound for the delay independent variant of the result is given in red, and we can actually achieve a lower error bound, significantly lower error bound for the delay dependent result. Okay, let me then conclude. So we have discussed different methods for reduction of delay systems, preserving the delay nature of the system, preserving stability and giving an error bound. There are also extensions to this approach for interconnected system and robust approaches. But let me close here and thank the collaborators with whom I've worked on this. So the decomposition approach has been worked together with Mim Michiels of KU Leuven and Bart Besseling of Rijksuniversiteit Groningen in the Netherlands. And the work on the balancing for DDE has been done by Sajjot Naderi, PhD student at the TUE, Bart Besseling, and also Antoine Sayet of Centraal Supélec. So thank you very much for your attention.
Well, thank you very much, Nathan, for this very nice talk.